Welcome to this lecture. My name is Mark Scythian. The date today is October 7th, 2025. So if you're working in aircraft maintenance and you're charged to task the construction of a hat channel sheet metal layout, stay tuned and we'll go over all the details so your project or testing is successful. So the first thing before we even attempt to go and bend sheet metal, we can only bend, we can never unbend. So making your first bends, starting with the 90-degree hat channel on the left, we'll have to start at the upper tier as the first bend, and then the other side of the upper tier, either or side, followed by the outboard sides, second to last. Because if you were to start bending the outboard sides, then you could not fit the sheet metal piece into the sheet metal brake, and then you'll have to redo it. So the first thing we have to do is look at the bend schedule here in black, and the sheet metal width is constant. So you'll have to break the sheet metal bend into components. So we'll break up the sheet metal bend into these given layout components. So the actual working length is known as the mold length line. This includes the projection of the bend on both the horizontal and vertical axes, called the setback. So if we were to subtract the setback from the mold length line, we would then get the flat value. We then add that to the bend allowance, the actual circumferential metal derived of a circle, its circumferential distance. This is known as the bend allowance. Then we would add this to the flat 2, bend allowance 2, flat 3, bend allowance 3, flat 4, bend allowance 4, and then flat 5. But we're going to start from the left and go right here. So we're taking it out of some unbent sheet metal section with constant width. So we have to cut the correct length that will then bend into the 90-degree hat channel. And remember, you can bend, but you cannot unbend. So all we're trying to do is invoke or implement these bend allowances with a sheet metal brake. And so that is a controlled bend, which then implements a controlled bend without cracks or stress risers. So the calculations part is as follows. We have to first label our components: flat 1 plus bend allowance 1 plus flat 2 plus bend allowance 2 plus flat 3 plus bend allowance 3 plus flat 4 plus bend allowance 4, and then finally flat 5. So we'll call the working lengths, including the projection of the bend on the vertical and horizontal axes, as the mold length line, the finished. So we have the first one at 1.25 inches. Then we have the vertical projection upward on a 90-degree bend, mold length 2, mold length line 2, and then mold length line 3. And again on the other side, mold length line 4. Then we have mold length line 5 to complete the bend projection. So here's our unbent sheet metal section. And then we have a metal thickness, in this case, of 0.064 inches. So the mold length line minus the setback projection is equal to the flat. That's the formula we're looking for to calculate the flat lengths. So what is the setback, the SB? This is the metal thickness plus the bend radius times the K constant for the degrees. 90-degree bends have a K constant of 1.000. So that's a coefficient of bend from the neutral axis point of the partial circle of radius. So the setback is equal to the metal thickness, 0.064 inches, plus the bend radius. So what is the bend radius? This is a ratio of the degree of bend of 360-degree circle times the designated units, 1 unit. So in this case, we're using the US system of measure. It's in inches, so 1 inch. So this is a bend radius of 0.25 inches for a 90-degree bend, times the K constant for a 90-degree bend, 1.000. So we calculate 0.314 inches is the setback. So this setback will be constant throughout the 90-degree hat channel because all bends here are 90 degrees. So now we are able to calculate all the flat values. So the first flat here is the mold length line minus the setback, but we only have one setback on the left outboard section. The vertical section we have 2 setbacks. The horizontal upper section we have 2 setbacks. The other vertical projection we have 2 setbacks, and the last outboard we have 1 setback. So we can check how we would calculate that before making the final calculations. So you notice the symmetry. Flat 1 and 5 are synonymous. Flat F2 and F4 are synonymous, and then F3 is by itself. So now we can make the calculations. All right, so now in order to calculate the unbent length, we now have to know what the bend allowance is, the actual circumferential distance of the bend, which is a derivative of a circle, but it's not a perfect quarter circle. So there is a formula we can access. So let's scroll down here for some room. Here in purple is the bend allowance equation. We would take 1/2 the metal thickness as one quantity. Then we would add this to the bend radius and then bracket the entire product sum calculation and then multiply this times the constant of 2 pi. And then this entire value, we would divide it into 4. So the easiest way to calculate this bend allowance is to break up the steps. So we will take 1/2 the metal thickness, 0.064 inches. So we get 0.032 inches. Then we would add this to the bend radius, 0.25 inches. Then we get 0.282 inches. Then we multiply that value times 2 pi. So we get 1.772 inches, and then we divide that value into 4. So we have a bend allowance equal to 0.443 inches. which is the partial circumferential derivative of a circle, but not a perfect circle. So we use this equation here. So scrolling back up, we now know our bend allowances are constant because all curves on the 90-degree hat channel are 90-degree bends. So to take the components that make up the bend schedule, this is the first flat, flat 1, plus bend allowance 1. You can see it, flat 1 plus bend allowance 1, plus flat 2 plus bend allowance 2, plus flat 3 plus bend allowance 3, plus flat 4 plus bend allowance 4, and then finally plus flat 5. So now we can just implement the information. Let's go back down here a little bit. Flat 1.936 inches plus our constant bend allowance, plus flat 2, plus bend allowance 2, flat 3, bend allowance 3, flat 4, plus bend allowance 4, and then flat 5. So when we add all these up, we get 5.51 inches is the unbent length. However, to interpret that correctly with respect to aviation maintenance structural tolerance, we have a 1/32 plus or minus tolerance in aviation maintenance. So that is 0.03125 inches. So if we were to subtract this value, we could, without even doing the calculation, know that it rounds to 5.5. And that is not simply just a significant digit mathematical calculation, but it is with respect to the FAA requirements as per AC 43-113B. So legally, it would suffice as 5.5 inches unbent length. So if you put that in the structural layout calculations on the paperwork, it would pass inspection. So now, how do we bend this unbent sheet metal piece? We start with bending at point 1, so we have to bend right here. Cannot bend anywhere we want. We have to bend at the start of bend allowance 3. So what we have to do is translate what the equivalent distance is from the right side here to this first point here. So we have flat 5 plus bend allowance 4 plus flat 4 plus the bend allowance 3. So I'll just write in the values here so we can save time, but it's taken from the list below. So we can zero out the right side here on the sheet metal section. So maybe your brake is right here and you'll start feeding it in on the right side. So all that the brake is doing is putting these controlled bend allowances in without cracks or stress risers. So that's why you need the sheet metal brake. So we have flat 5 plus bend allowance 4 plus flat 4 plus bend allowance 3. Then we stop. What is the summation distance? So that is flat 5 plus bend allowance 4 plus flat 4 plus the bend allowance 3. So that's 2.394. And again, you can add 0.3125 and it's going to exceed 2.4. So you're good. 2.4 is the legally designated start point of the first bend from the right side inward. So you'd start your bend right here, and this section would curve into this bend allowance right here. Because these are symmetrical with respect to the right outboard and the left outboard, you can go, after making this bend here, you'll get a long right angle. You can flip it around and feed the other side of the sheet metal section into the brake, and then you bend right here. You would bend not here, but you would bend right there, because this will curve, this metal will go from straight into the curve. So now you got this really awkward, long, upside down U bracket, like that. So then you can turn it over to its side. So after making these two bends, you get this shape. Now you can bend it this side. And depending on what kind of brake you're given, you probably have a hat channel brake for more than two bends. So you'll be able to slide this through and make the bend here. So the third bend is right here. So you'd have to bend that downward in this case if it's to the right. So where does that starting? You start from the edge. It's going to be flat 5 plus bend allowance 4. So what is that in value? 0.936 inches. That's flat 5 plus bend allowance 4, or they're all equal, so 0.443. So you get a value of 1.379. So you could add the tolerance to it to see if you can round up, and it goes above 1.4, so just use 1.4. That's the legal limit, or it's within legal limits, that is the tolerance. So that's where your third bend will be, right here. So you have bent this downward, these two, you have a bracket, then you have to bend this one upward. And then you do the same thing on the other side. So now you've bent the hat channel outward and you're finished. So this one here is a hat channel that's 135 degree hat channel. So just to keep things simple and on point, I'm going to make another video and it will cover this one. But remember that these are not 90 degree bends. These are 135 degree bends, and this obeys the fundamentals of geometry. So we have a 135 degree bend, two of them. And so if we take the supplementary and complementary of a symmetrical 135 degree hat channel bend, then the other sides are 135 as well, unless otherwise specified. So whenever we're bending non-90 degree angles, you can use the K chart, the coefficient of bend from the neutral axis. And this is available in the structural repair manual, or if you're taking a test for your A&P license, the AC 43-1B Acceptable Techniques and Practices Handbook has the K chart in the sheet metal section. So you're allowed to use that during a test, and you're absolutely going to use that in the shop. There's usually a K chart in the structural fabrication shop. So you'd go down here to 135 degrees, and that's 2.414. And then you would apply it into the setback equation to calculate what the setback is from these mold length lines. So feel free to pause the video and absorb the step-by-step information. In the next video, I will cover the 135 degree hat channel. Thank you for watching this lecture, and I'll see you in the next video.